Modulus of complex numbers.
Welcome to another episode of King Solomon and David Picozzi on algebra. So today we'll be dealing with equality, modulus, and argument of complex numbers. The equality, modulus, and argument of complex numbers. Now, when we say two complex numbers are equal, what do we mean? So let's assume that z1, which is x1 plus y1i, and z2, which is x2 plus y2i, be complex numbers. You've already established the fact that anytime you have a complex number, x is the real part of the complex number, and y of the I, which is the imaginary part of the complex number. Now, if these are the same, then z1, that's the complex number z1 will be equal to the complex number z2 if and only if the condition is that the real parts should be equal. X1 should be equal to x2 and y1 should be equal to what? Y2. So now if I have a complex number, say I have z1 which is 3 plus 6i, and I have z2, and z2 is also giving me 3 plus 6i, then I can say z1 is equal to z2. So for instance, if I ask to find it, we have a complex number which is z1 and it's 4 minus 5i, and we have z2 which is maybe, let's say, 4 plus, let's say, a plus 2i. So you have an example of such nature, and they ask you that the condition is that if z1 and z2, if z1 is equal to z2, then you should find a. If z1 is equal to z2, then you should find a. So what should come into is that from here, you realize that the real part, they are the same. So the imaginary part should also be the same. So therefore, the negative 5i should be equal to a plus 2i. So the I will take the I away. So we get negative 5 should be equal to a plus 2. So if you do this, you are getting a to what? Negative 7. So if a is negative 7, and you put the negative 7 here, you get z2 as 4 plus negative 7 plus 2i. And that will finally give us 4 plus 4 minus 5i as the same as what? As z1. So this is the condition for equality. Let's look at the modulus and the argument of the complex number. Now, taking the component notation of the complex number, so the modulus is here. So if you take the complex notation of a complex number, the component notation of a complex number as this, then the modulus of a complex number z, the modulus of this complex number z is represented this way, and that is simply equal to the square of the real part plus the square of the imaginary part, all under a square root. So it's simply equal to the square of the real part plus the square of the imaginary part, all under what? A square root. But why is this so? This is so because if you consider the eigen diagram, so if you take the eigen diagram, this, let's say, is point O. It will have a coordinate of what? 0, 0. And let's say there is a certain point within the first quadrant of the eigen diagram, and that point describes a complex number, which is xy. So now to find the modulus of from the origin, so the modulus is always with respect to the origin of the eigen diagram. So to find that modulus, that is this length, the same as this length. This length. So now the difference between here is what? Y minus what? The origin, and the difference here becomes what? X minus what? The origin. So to consider this as ZO, so magnitude of the ZO will simply become what? The square root of what? X minus O all squared plus Y minus O all squared. So the magnitude of the Z2, because it's already the same as what? The magnitude of the complex number, that gives what? The square of the x plus what? The square of the r over here from the eigen diagram. Now realize that when you do this, there's a certain angle that that's the complex number, or the modulus of the complex number, the length of the complex number will make with the positive axis. There's a certain angle it will make with the positive axis. Now that angle over there is what we call the argument of the complex number. That angle is what we call the argument of the complex number. So therefore, argument of complex number, the argument of complex number is always represented by ARZ. It's always equal to that angle over there. And I realize that if you draw the eigen diagram, and this is the Z component xy, this angle here, y and x, you realize that to find the argument of the complex number, which is equal to the angle, is equal to the tan inverse of opposite over adjacent. So that's the tan inverse of what? X, y on x. So this is how you can find the argument of a complex number when we are given what? A complex number. This is how we can find the argument of that particular complex number. I want us to take some examples, but before we take the examples, always mind you that the angle argument, the origin, the quadrant the angle falls within it matters a lot, because when you draw your eigen diagram, take note. Here is what? Is pi. Here is positive pi on 2. Here is negative pi, and here is negative pi on 2. Here is your first quadrant. Here is your second quadrant. Here is your third quadrant. Here is your fourth quadrant. So take note on something here. Very, very important. It will really help you solve a lot of questions with this diagram. So anytime you have the real part, so let's say the real part is here, which is the x, and the imaginary part, which is the y. So anytime you have a complex number with a positive real part, you have a complex number with a positive real part and a positive imaginary part. That is to say, the x is positive and the y is positive. Then the argument of that particular complex number will fall within what? The first quadrant. The argument of that particular complex number will fall within the first quadrant, and it will be in the range. This is the first quadrant, so it will be in the range of what? Pi. So that angle will be in the range of pi to what? Pi on 2. Take note. And this is the first thing you are supposed to take note. The second point you are supposed to take note. Anytime you have the x part of the imaginary to be negative, and you have the y part should be positive, then the argument or the angle theta will always lie within what? The second quadrant. The angle will always lie within the second quadrant. What I'm doing here is very important. Follow, because when you are solving questions, you understand it. We will lie within the second quadrant. Now, when you lie within the second quadrant, the range of it is pi on 2, the argument z, in between what? Negative pi. So the range of it ranges from what? Pi on 2 to what? Negative pi. Take note. Now, the third point, if x is negative and the y value is negative, then our argument of the complex number, which is the same as the angle theta, will now lie within the third quadrant. And when it lies within the third quadrant, the range is simply, this is the third quadrant. So we start from what? Negative pi, argument of v, to what? Negative pi on 2. Okay, and the last one is when you have the x to be positive and have y value to be negative. Then your argument this should be theta should lie within the fourth quadrant. Should lie within the fourth quadrant. And if it is within the fourth quadrant, then what we're having is that our range should range from what? Negative pi on 2, the argument z, to what? To pi. But anytime we want to find the argument z, the angle, anytime we want to find it, most of the times, if you want to find the angle, you have to measure from the positive axis. If you want to find the angle, always or most of the time, measure from what? The positive axis. So let's take two or three examples, and you actually understand how we go about this. Okay. So now, this is the first complex number. We have z which is equal to 2 minus 3i, and the b, the second complex number, which is z equal to 3 plus 4i, and the third complex number z, which is equal to minus 3 plus 4i. Okay. So now, since we are having these three questions, let's quickly go through them and find our modulus and argument. So the first part, 2 minus 3i. So it's the same as I plus yi, and you say our modulus is simply what? The root of the imaginary, describe the imaginary part, and the y is here. So here x is what? Is 2, and our y is negative 3. Are you getting it? Okay. So now therefore angle here becomes what? 2 squared plus negative 3 squared. And when you do this, you get root of 13. So our argument is giving us root of 13. But how do you find our modulus is giving us root of 13? How do you find our argument? Our argument, which is the same as the angle theta, is equal to the tan inverse of y on x, and the y is what? Negative 3 on x, which is 2. And when you do this, you get negative 56.31. Negative 56.31 degrees. Now, this argument here, let's look at the range. So, the range of the argument, where can this argument be found? The range of this argument is that it is found in what? The fourth quadrant. So when you say the x is positive and the y is negative, then it is found in what? The fourth quadrant. And in the fourth quadrant, this is it. So yes, pi on 2, pi on 2, negative pi. So this is the fourth quadrant. So that means if it's found in the fourth quadrant, the angle theta here should be pi on 2, negative pi on 2, and the argument z, pi. And when it's here, and you're supposed to measure from the positive axis. So when I'm measuring from the positive axis, this is the angle. So the angle here now becomes 56.31 degrees when I'm measuring. So therefore, the angle theta measuring from the positive axis should read 56.31 degrees, not negative 56. So if you don't know the range to which it is reading, you always leave your answer in what? Sometimes in negatives, and that will not help. So you should know the range. So this is reading here. You have to measure from the positive axis, and the positive axis is here. That is this part of the pi value. So measuring from this part to the complex number is what? 56.31 degrees. Okay. Let's look at the second one. The second aspect. B. So which is 3 plus 4i. So here the x is 3 and the y is 4. So to find the modulus, which is simple, the square root of what? 3 square plus what? 4 square. When you do this, you are getting root of 25, which is equal to what? 5. Okay. Now how do you find our argument? The argument of c, which is the same as the theta, is therefore equal to the tan inverse of the y, which is 4 on 3. And when you do this, you are getting 53.13 degrees. Okay. Now, how do you find the range? So the range of this argument, the range of this particular argument is s is positive, y is positive. So if s is positive, y is positive, then it will lie within the first quadrant, which is the first quadrant. So that's pi on 2, negative pi on 2. So this is the first quadrant. So that means the range of this is pi argument of z pi on 2. So now calculating the angle from the positive axis, measuring for the positive axis, this angle is what we calculate as the argument. That's what 53.13 degrees. Okay. Now the C part, or the last part, we are given negative 3 plus 4i. So from here, x is what? Negative 3, y is 4. So the argument z becomes negative 3 squared plus 4 squared. And that will give you root of 25, which is 5, equal to 5 units. Okay. So this is the argument. This is the modulus, sorry. How do you find the argument then? The argument here now becomes the argument z, which is the same as the theta, becomes the tan inverse of here is 4 and here is negative 3. So if you do the tan inverse of this, you are getting 53.13 degrees. 53.13 degrees. Okay, so when you get this 53.13 degrees, okay, 53.13 degrees, what you have is that want to know the range of the angle, and the range of this angle will lie between, because x is what? Positive, y is what? S is negative, y is positive. So if x is negative and y is positive, then it lies within what? The second quadrant. So this is it. Our pi on 2, our minus pi on 2. So if it is lying within that range, then this is the second quadrant. So then the angle or the argument of the z will lie between this pi on 2 and negative pi. Pi on 2 and negative pi. So calculating the angle from the positive axis. Calculating the angle from the positive axis is from here to this point. So the angle we got here was what? 53.13. But take note that if we are calculating from the x positive axis, then it's 90 plus 53.13, and that will give us 90 plus 53.13, and that gives us 143.13 degrees. Okay, so this will bring us to the end of the modulus and argument of the complex number. Thank you.